Hi guys, welcome to my 12th lecture on solving ordinary differential equations. Today we want to look at Laplace transforms and how they can be applied to solve higher order linear differential equations. Right. I'll begin by introducing the concept of what a Laplace transform is and some of its very important properties. And then we'll go ahead to look at how to calculate Laplace transforms of some basic functions, which are going to be building blocks for an application to solving differential equations. Right. So in the next lecture, we are going to focus on using the skills that we are going to acquire from this lecture to solve differential equations. All right. So what is a Laplace transform? A Laplace transform is classified as an integral transform, meaning that it uses an integration process to convert or to transform a function from one domain into another domain. Right now, it takes us from a function. Conventionally, we use t. Right, so we have a function in terms of t, but a function could be in terms of any other variable, and then it takes us into a function in terms of s. Right. Now, the domain of the function for which we are calculating the Laplace transform, or at least the domain of interest, is from 0 to infinity. Right. So we are only concerned about the behavior of the function on the positive real axis. Okay, and then we apply this integral process to convert it to a function in terms of s. Right. Now notice that because this integral is with respect to t, which is the independent variable in the function, right? The result of this integration, this improper integral, is going to be a function in terms of s, because you are going to eventually integrate out the t, right, from this improper integral here. Okay, so if we're able to perform this calculation, right, then the resulting function that we get is a Laplace transform. Okay, now the domain of this Laplace transform is any value of s for which this improper integral converges. Right. So if there's some value of s for which it approaches infinity, then that is not going to be in the domain of the Laplace transform. Okay. Now, conventionally, if we calculate the Laplace transform of a function little f, the transform is denoted by capital F. Okay, that is just the convention. So if your function is g, its transform is going to be capital G. Okay, and then we're going to use that convention throughout. Right. Okay, so we can do this. We can do this for a function f, and the goal is to be able to use this transformation process to solve ordinary differential equations. Right. Now, what we are going to discover down the line is that this integral transformation process, when applied to derivatives, right, makes the derivative process very, very straightforward, and essentially allows us to convert differential equations into algebraic equations. We're going to see that in the next lecture, and so the Laplace transform allows us to go from solving an equation involving derivatives to just a regular algebraic equation that we would solve, like in college algebra, something like that. And that is really the power of the transform. Okay, so what we're going to do today is just to try and understand how this transform operates. How do we actually perform this improper integral? What kind of functions can we at least guarantee that they will have? What kind of functions can we guarantee that this integral will converge for? Right? In other words, what kind of functions will have a Laplace transform or a transform not? So we're going to look at different groups of functions that have Laplace transforms. We're going to compute their Laplace transforms, we'll see how we can use them later on to solve differential equations. Okay, so so let's dive in and try and apply this integral process to calculate the Laplace transform of e to the at. So solution. All right, so the Laplace transform of e to the at by definition is the integral from 0 to infinity e to the minus st e to the at dt. Right? So this is the integral from 0 to infinity e to the minus s minus at dt. Right? Now remember that the improper integral is just a limit as the upper the upper limit approaches infinity of an integral defined on the bounded domain. So we just take the left boundary to 0 to infinity to derive the improper integral e to the minus s minus a. Hopefully you remember this from Calc 2. All right, so now we can perform this integral. This is the limit as b approaches infinity. This is minus 1 over s minus a e to the minus s minus a t using the fundamental theorem. And now we have 1 over s minus a, the limit as b approaches infinity. We have 1 minus e to the minus s minus a b. Okay, so now let's take a closer look at this limit here. Right. Now, notice that if s is greater than a, then s minus a is positive, which means that as b approaches infinity, this is going to approach 0. Right. So that is true as long as s is if s is positive, s minus a is positive. Right. Of course, if s is equal to a, then this is just 1, and the whole thing is and the whole thing in brackets here is 0. Right. But then, of course, if s is equal to a, this part here is not defined. Okay. And if s is less than a, then this is going to be negative here, right? Which is going to take us into infinity. So if s minus a being positive, and if that happens, then the Laplace transform of e to the at is 1 over s minus a. And this is defined for s greater than a. So notice that we've gone from an exponential function to just a rational function with some specific domain, right? And that is really what the Laplace transform is. It takes us from one function to another, right? And that simple, process of changing the nature of the function in this way is going to prove itself to become very, very useful down the line. Okay. All right. Now, there's a very important property of Laplace transforms which we want to look at. This is called the linearity of the transform, and it's based on the fact that the Laplace transform is really an improper integral, and because integrals are linear operations, and so the Laplace transform of a constant times a function plus a constant times another function is just a constant times the transform of the first function plus the constant times the transform of the second function. So this is what we term as the transform being linear. In other words, it kind of distributes through the sum here. Right? So the Laplace transform of a linear combination of two functions is a linear combination of the transform of the two functions, is how you can describe it. Now we're assuming here that the functions f and g both have Laplace transforms. Otherwise, this will not be well defined. Okay. All right, so let's see why this is true. It should be obvious to you, but let's go through it. So the transform of a times f of t plus b times g of t, right? By definition, this is the integral from 0 to infinity, e to the minus st. We have a times f of t plus b times g of t. And then if we distribute the integral through, we have the integral from 0 to infinity, e to the minus st, a f of t dt, plus the integral from 0 to infinity, e to the minus st, b g of t dt. Right, and then we can always take the constant out. So we have integral from 0 to infinity, e to the minus st, f of t dt, plus b integral from 0 to infinity, e to the minus st, g of t dt. And by definition, this is, since the Laplace transform of f and g exists, we know that these improper integrals converge. And so we have a times the Laplace transform of f of t plus b times the Laplace transform of g of t. And that shows the linearity property here. Okay. Now we're going to use this property to take the Laplace transform of sums of functions. Right, so that if we can find, if we can identify, the Laplace transform of some basic functions, then if you take, this is basically saying that if you take any combination of functions, you can just apply the Laplace transform for each of those functions individually, and the sum would be the transform of the original combination. Okay, so this is a very important property going down the line. Now there's a similar but distinct property for products. It doesn't quite work this straightforward. So we're going to look at that sometime in the next lecture. How do we deal with the Laplace transform of products? Right. But for now, we'll stick to the Laplace transform of sums. Okay. So now that we kind of have a feel for what is going on, we are applying an integration process to take one function, to put one, to change the form of a function, right? And of course, its domain as well. The question that we want to ask next is that, can we do this for any function, right? And the answer is no. And here's why. Okay. All right. Let's define what it means for a function to be of exponential order. Right. Let me just explain this. Okay. Now, the most important thing for a function to be able to have a Laplace transform is that the integral from 0 to infinity e to the minus st f of t, this integral must be finite, which means that it converges. Okay. If this integral is finite, then we know that the transform exists, because we have to be able to have, the transform must be able to give us a real number. Okay. And so what we're going to do is that we're going to look at conditions on this function f of t that will ensure that we can compute this integral. Okay. And one of those properties is the idea of the exponential order. Okay. The exponential order is a restriction on how fast the function can grow. Okay. And so if we consider an exponential function here, and let's say that this function is defined as m e to the ct, where m is some positive real number, and c is also a positive real number according to our definition here. So let this be an exponential function. Then we're going to say that a function f is of exponential order if after some time t, the function is always going to lie below this exponential function here. So this is my function f of t. Right? And it's going to always be bounded about by the exponential function for all time. For all time. So it's never going to exceed the exponential function. Okay. Now it may exceed the exponential function, before this time t, but after this time t, its growth is never going to grow faster than the exponential function, me to the ct. Okay. Now if this happens, then we say that the function f is of exponential order. Right. Okay. So how does this help us to guarantee that a function has a Laplace transform? Okay, so here's the theorem for the existence of the Laplace transform. Right. Now, if we can confirm that our function is piecewise continuous, right, for all non-negative time, and if the function is of exponential order as t goes to infinity, then we can say for sure that its Laplace transform exists. And in addition, we can verify that the function, the Laplace transform, has a horizontal asymptote. Okay. So first, we are going to show that piecewise continuity plus exponential form as t goes to infinity implies that the transform exists. Okay. And then we'll go ahead to verify this extra property here of the transform. Okay, so let's assume that a function f is piecewise continuous. Now remember that if a function is piecewise continuous on an interval, then it means that you can always find a subinterval, or you can find a partition of that interval, right, within which the function is continuous. And at worst, the function has a jump discontinuity at the endpoints of those subintervals. So this is what I mean. So this is piecewise continuous. If you are, let's say that you are piecewise continuous over the interval AB, right, then what it means is that I can construct some partition of my interval AB such that within each partition in the open interval, my function is going to be continuous. Within each open interval. And at the endpoints, the worst thing that can happen is that my function has a jump discontinuity here, and 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 a jump discontinuity there. Right? That's the worst thing that can happen at these endpoints, that the function will jump. Okay, it cannot approach infinity or minus infinity at these endpoints here. Okay, so if that happens, then we say that the function is piecewise continuous over, the interval AB. So the same thing applies for being piecewise continuous on the non-negative real axis. It means that we can construct some partition of the non-negative real axis for which the function is continuous in subintervals, and at worst, it has a jump discontinuity at the endpoints of the intervals. All right, so that's what it means to be piecewise continuous. We know what it means to be of exponential order. It means that we can bound the function above by some exponential function of this form, right, for all values of t greater than capital T. Okay. All right. So how does this imply that the transform exists? Okay, let's think about this. Okay, now if a function is piecewise continuous over an interval, say over the interval AB, right, then clearly, since the function can only have jump discontinuities at the endpoints, we should be able to find an upper bound for our function, because the function is not going to approach infinity anywhere in my interval. So there should be some constant that will be greater than every value of the function. Is what I'm saying here. Okay, because it's piecewise continuous, right? And so you know, assumption 1 implies that my function f of t is bounded above on the interval 0 to t, right? That I can find, in other words, I can find some positive number n such that my function is always less than n for t between 0 and t. Actually, this will even be over the whole interval. Okay, so if it's piecewise continuous, we are guaranteed that this can happen, right? That we can find this function above. Okay, now of course, if it's of exponential order, then we know that this is true. That beyond this point t here, that the function is bounded above by this exponential function here. Okay, and so the two conditions, being piecewise continuous plus being of exponential order, implies that my function is bounded above by some m star e to the ct, right, where m star is the maximum of n and m. Okay, so notice here that I could have, you know, written this upper bound as n times e to some ct, or to e to the c even, right? Okay, I could have written it this way, right? So in other words, I'm taking, right, since it's bounded by, you know, n e to some t for all t between 0 and capital T, and it's bounded above by m e to the ct for t greater than, you know, t, then on the entire positive, or the entire non-negative real axis, I can say that the function is bounded above by m star e to the ct. Right? Okay, so then if that's the case, now let's look at the integral from 0 to infinity, the absolute value of e to the minus st f of t, right? Clearly, this is the integral from 0 to infinity. Since e to the minus st is positive, this is the absolute value of f of t, dt. Right? Now we've just verified that my function is bounded above by m star e to the ct, and so this integral has to be smaller than or equal to integral from 0 to infinity e to the minus st m star e to the ct dt. Right. Now I can take my constant out, so this is m star integral from 0 to infinity e to the minus s minus c t dt. Right. Here, right, and as long as s is greater than c, I can perform this integral here. So if s is greater than c, right, then and the integral from 0 to infinity m star e to the minus s minus ct. Right, this will be m star over s minus c, right? And then we have minus e to the minus s minus ct. This is 0 to infinity, and this is interpreted as a limit here. Right? And then this gives me m star over s minus c, because this, since s is greater than c, this is going to be positive. And so if we take the limit as t goes to infinity, this is going to go to 0. And then, of course, when t is 0, this is 1. Right? And so this integral is finite. Since m star is some positive real number, this is finite. Right? Which means that this integral here converges. Okay, so the integral is convergent. Now, how does this relate to the Laplace transform? So, right now, the absolute value of my Laplace transform, e to the minus st f of t dt, is less than or equal to the integral from 0 to infinity, the absolute value of e to the minus st f of t dt. This is true, right? And so since this integral here is finite or converges, and the absolute value of my Laplace transform is smaller than that integral, it implies that my Laplace transform converges, right? Which means that it exists because it's finite. The integral converges. Okay, and so it is sufficient for a function to be piecewise continuous and of exponential order for it to have a Laplace transform. Okay, now what this theorem is not saying is that the only functions that have Laplace transforms are those that are piecewise continuous and of exponential order. That is not what it's saying. So this is not a necessary condition for existence of Laplace transform. It's just a sufficient condition. Okay, so that we could, we could construct some functions that, are not piecewise continuous and are not of exponential order that have Laplace transforms, right? But that's not what we are interested in. All we want to be able to say is that, well, we want to have a way to guarantee the existence of the transform. And so this sufficient condition gives us that guarantee. And as long as we can verify that these two conditions are true about a function, then we have some confidence that it has a Laplace transform. Okay, so now we know that piecewise continuous functions of exponential order have Laplace transforms. Okay, now the idea of the Laplace transform always having a horizontal asymptote is because the integral from 0 to infinity e to the minus st f of t dt, okay, the absolute value of this is less than or equal to, of course, the integral from 0 to infinity, the absolute value of e to the minus st dt. Right, which we have just shown to be equal to m star over s minus a. And we know that this is always going to be positive because it's the absolute value, right? And so now if I take the limit, as s approaches infinity, I have that the limit as s approaches infinity of the absolute value of the integral from 0 to infinity e to the minus st f of t dt, right? This is going to be positive. This is the absolute value of the limit as s approaches infinity. Which is less than or equal to the limit as s approaches infinity of m star s minus a. Okay. Now clearly, as s approaches infinity, this limit here approaches 0 because the denominator grows without bounds. And of course, as s approaches infinity here, our left, the left side of this inequality here is also 0. And so we can conclude by the squeeze theorem that really there's only one thing that can happen to our function, at least in absolute value. So we have by the squeeze theorem that the limit as s approaches infinity, the absolute value of the integral from 0 to infinity e to the minus st f of t dt is 0. Okay. Now, of course, from Calc 2, remember that if an integral or if a function or a sequence converges absolutely to 0, then it implies that the sequence converges to 0. Okay. And so this concludes our theorem that the Laplace transform, right, if you are able to construct the Laplace transform of some function, that transform will have to converge to 0 as s approaches infinity. So it must have a horizontal asymptote. Okay, so this is a good way to check when you calculate the Laplace transform of a function. You can always check to see if it has a horizontal asymptote on the s-axis. So if it doesn't have a horizontal asymptote on the s-axis, or if it doesn't converge to 0 as s goes to infinity, then it's not a Laplace transform. Okay. All right. So now let's go through a few functions and attempt to confirm whether or not these functions have Laplace transforms. And then we'll proceed to calculate the Laplace transforms. All right. So the question here is, which of the following functions is of exponential order? Right. Which of the following functions is of exponential order? Now we know that these functions, at least we know that these functions here are piecewise continuous. The secant is not piecewise continuous because it has infinite limits, at certain discrete points. Wherever the cosine is 0, the secant has an infinite limit. So this is not piecewise continuous, right? And so if we can show that all of these functions are of exponential order, and since all of these functions are continuous, which means they are piecewise continuous, then it shows that all of these functions have Laplace transforms. Okay. And so what we're going to do is to then compute the Laplace transforms of these functions. And you can have that, as a reference. Okay, so let's go ahead and see. Is e to the at of exponential order? Yes, because this is less than or equal to e to the at, right? Which is the very definition of exponential order, where here my m is 1 and my c is a. Okay, so this is definitely of exponential order. T to the n, right? Now recall that e to the t, right, is 1 plus t squared on 2 factorial plus t cubed on 3 factorial, and so on. You have some tn on n factorial, on and on and on and on and on. Okay, and so clearly t to the n, which is just one of the terms, in the exponential, in the Maclaurin series of the exponential function, is going to be smaller than e to the t for all t. Right? And so this is since it's bounded above by some exponential function, we know that it is of exponential order. Exponential function with a positive growth rate. Okay. Then 3, cosine of AT, right? Well, clearly we know that cosine of AT, right? This is less than or equal to 1. Right? And 1 is the same as 1 times e to the 0 t. Okay, so this is clearly of exponential order for all time, for all positive time. So it's of exponential order. Now let's look at e to the AT, the sine of AT. Again, if you take the absolute value of this, this is less than or equal to e to the AT, right? So clearly this is of exponential order if we take m to be 1 and c to be a. This is true for all t positive. Okay. It's true more generally, right? This is true for any real number t, but remember that we are only focused on, at least for exponential order, as we're only looking at the independent variable approaching infinity. So it's okay that it just be positive, that t just be positive here. But then the fifth one, so the secant of AT, this is 1 over the absolute value of the cosine of AT, right? And we know that this is unbounded when t is pi over 2a times n, where n is odd. Right? And so because it's unbounded at these time points, right, we cannot bound it above by some exponential function at these points. And so this is not of exponential order. Okay. So what this essentially tells us is that we can, since all of these functions are continuous, we can actually calculate their Laplace transforms. Build up a reference for Laplace transforms that will be useful as we go forward. Okay, so find the Laplace transform of the sine of AT and the cosine of AT. So let's look first at the sine. Laplace transform of the sine of AT. Right. Now remember that the sine of AT, right, can be expressed as e to the AIT minus e to the minus AIT over 2i. Right. So this is the same as 1 over 2i. The Laplace transform, since it's linear, e to the AIT minus the transform of e to the minus AIT. Okay, so let's focus on computing the Laplace transform of e to the AIT. By definition, this is the integral from 0 to infinity, e to the minus st, e to the AIT dt. This is the integral from 0 to infinity, e to the minus s minus AI t dt. Now if I integrate this, and I have minus 1 over s minus AI. Then we have here minus e to the minus s minus ait. Evaluated from 0 to infinity, so this here is a limit, right? And so this is minus 1 over, let's take this minus out, 1 over s minus ai. This is 1 minus the limit as b approaches infinity of e to the minus s minus ai of t. Okay. B here. All right. So let's take a closer look at this limit here. So recall that e to the minus s minus ai b is e to the minus sb times e to the aib, right? And so if we take the absolute value of e to the minus s minus aib, right, this is going to be the absolute value of e to the minus sb, e to the aib, which is going to be bounded by e to the minus sb. Okay. And so the limit as b approaches infinity of e to the minus s minus aib, right, this will be less than or equal to the limit as b approaches infinity, e to the minus sb, right? And as long as s is positive, so as long as s is positive, this limit here is going to go to 0. Okay, and so since this function here converges absolutely to 0, we know that it converges to 0, and so we have that the Laplace transform is 1 over s minus ai, where the only requirement is for s to be positive. Okay, and so by the same analogy, we can say that the Laplace transform of e to the minus ait is 1 over s plus ai, where s is positive. Okay. So now we can combine these two to find the Laplace transform of the sign. So we can say that Laplace transform of the sine of at, right, is 1 over 2i. We have 1 over s minus ai minus 1 over s plus ai. This is 1 over 2i. If we combine this into a single fraction, we're going to have, so this is s minus ai, s plus ai. So this is a difference of 2 squares, ai squared. And then up here we have s plus ai minus s minus ai. So we have 1 over 2i. Up here we're going to have 2ai divided by s squared plus a squared, because I squared is minus 1, right? And so 2i divides out 2i, and so we are left with a over s squared plus a squared, right? So this is true as long as s is positive. All right, so that is the Laplace transform of the sine of 80. Okay, now you can use the same idea to show, you can show that the Laplace transform of the cosine of AT, right, is S over S squared plus A squared for positive S. So it's defined for all S positive. Okay. All right. Now take note that this transform, right, as well as the transform of the sine, all satisfy the property that as S approaches infinity, the transform approaches zero. Okay. So if you have a rational function as a Laplace transform, then you must have that the degree of the denominator has to be greater than the degree of the numerator in order for it to be a valid Laplace transform of some function. Okay, so you can easily use that again to discard functions that are transforms and those that are not. This will be important down the line. Okay, so if we are done with the cosine and the sine, all right, now we want to look at how to compute the Laplace transform of power functions, so functions of the form t to the a. Where a is just some real number, right? So this, if we can find the transform of this, then we can find the transform of all polynomials, because polynomials are just, you know, in the case where a is an integer, polynomials are just linear combinations of these monomials, and we already know that the Laplace transform is linear, and so we can just take the transform of each of the terms and then combine them together. So to be able to find the transform of a power function, which is our goal here, we're going to need what is called the gamma function. Right? And the gamma function is defined by this integral. It's a function here. The domain is for all positive real numbers. So x. Now again, notice that this integral here is with respect to t, right? Which means that once we are done with the integration process, what we're going to have left is a function in terms of x, which is why this is gamma of x. And so the function is defined only for you know, positive real numbers, right? And it has this very important property which we are going to prove, almost like a recurrence relation here, right? That the gamma, so this gamma here is denoting the gamma function, of course. So gamma of x plus 1 is x times gamma of x. Okay, this is going to be the property that we are going to use to find the Laplace transform of a power function. Okay, there's also the property that gamma of 1 is 1. We are going to show this also to be true. All right. Okay, let's deal with gamma of 1 first, because that is more straightforward. So by definition, gamma of 1 is the integral from 0 to infinity e to the minus t. Right, and then since x is 1, this is just dt. Okay, and so clearly this is minus, you know, e to the minus t, 0 to infinity, right? And of course, as long as my, since I'm from 0 to infinity here, I know that this is 1 minus the limit as b approaches infinity, e to the minus b, which is 0. Right, so this is 1. So gamma of 1 is 1. So now let's compute gamma of x plus 1. Okay. And so by definition, this is the integral from 0 to infinity, e to the minus t, right? And then we have t, we have x plus 1 minus 1 dt. And that is the integral from 0 to infinity, e to the minus t. We have t to the x dt. Okay. Now we can apply integration by parts here. This is the limit as b approaches infinity. So we can define this over a finite interval and then apply integration by parts, since these are continuous functions. we know that on any finite interval, this integral is going to exist. Right? Okay, so let's focus on just the finite part of this. Let's focus on the integral from 0 to b, e to the minus t, t to the x dt. Right? If we apply integration by parts, this gives us minus t to the x, e to the minus t from 0 to b, plus x integral from 0 to b, e to the minus t, t to the x minus 1 dt. Right? And we can simplify this. This is going to be minus b to the x over e to the b, plus x integral from 0 to b, e to the minus t, t to the x minus 1 dt. All right, so now if we take the limit as b approaches infinity of this integral, right? Here, if we take the limit as b approaches infinity, right? Again, we have b to the x. X is some, not a positive real number. E to the b is always going to be bigger than b to the x. Again, because the exponential, if you expand out this e to the b, you're going to get all possible powers of b. And that sum is going to be larger than b to the x. B goes to infinity. This fraction is going to go to, this ratio is going to go to 0. Okay, so this goes to 0 as b goes to infinity. So we have 0 plus, as b goes to infinity, we have now an improper integral. 0 to infinity, e to the minus t, t to the x minus 1 dt. Okay, and then notice that this integral here is gamma of x by definition. Okay. And so what we have now is, this is gamma, this x, gamma of x. So we have shown that gamma of x plus 1 is x gamma of x. Okay. Beautiful. This is a very important relationship that we are going to exploit. Okay. Now, so this is true for any positive x. Right? Now, if x is an integer, there's a very important corollary of this theorem. One that you would find very, very interesting. Okay, so if x is a positive integer, so let's call it n, then we have that gamma of n plus 1 is n times gamma of n, right? Okay, and then this is the same as n times gamma of n minus 1 plus 1, right? That is the same as gamma of n. And then if we apply the same relationship here, right, gamma of n minus 1 plus 1, this would be n times n minus 1 gamma of n minus 1, where we have applied it here, applied the same relationship here. So if we keep breaking this down, okay, this will now be n minus 2 plus 1, right? And so this will give us n times n minus 1, n minus 2, gamma of n minus 2. And then if we write this as n minus 3 plus 1, we have n times n minus 1 times n minus 2 times n minus 3 times gamma of n minus 3. And so we can go on and on and on, and eventually, as we keep reducing this all the way up to 1, we're going to have n times n minus 1 times n minus 2 times n minus 3 times and so on. And this is n factorial. And so we are saying here that gamma of n plus 1 is n factorial, right? So if we restrict x to be an integer, then the gamma function is really just a factorial operation, right? But then it's bigger than that because x doesn't have to be an integer, right? So we can think of the gamma function as some generalization of the factorial operation for integers, right? It's an extension to all real numbers. Okay. All right, so we'll keep this property also in mind. And then we're going to use the gamma of 1 is 1, right? Now, we can also show that gamma of 1/2 is the square root of pi. I'm going to leave that for you as an exercise. So this is also going to be important going forward. And then, of course, the more general form, gamma of x plus 1 is x gamma of x. Okay, so with these identities, let's go on to calculate the Laplace transform of a power function. So we want to find the Laplace transform of t to the a. We are assuming here that a is greater than -1. That will become clear very soon, right? So by definition, this is the integral from 0 to infinity e to the minus st. We have t to the a dt. Okay. Okay. So now let's make a change of variable. Right. If we set u to be minus st, then du is minus s dt. So we have minus 1 over s du is dt. Right. Now, of course, this also implies that, let's make this easier for ourselves. Let's set u to be st. So that we can avoid those negatives flying around here. Okay, so then from here, I can also say that t is u over s. Okay, so let's change variables from t to u. And then I have 1 over s, integral from 0 to infinity, e to the minus u. My t is u over s to the a du. So this is 1 over s a plus 1, the integral from 0 to infinity, e to the minus u, u to the a du. Okay, now I can write this as 1 over s to the a plus 1, integral from 0 to infinity, e to the minus u, u to the a plus 1 minus 1 du. Right. And now if you refer to the definition of the gamma function, notice that this integral here is just gamma of a plus 1. Okay. So that implies that the Laplace transform of t to the a is actually gamma of a plus 1 divided by s to the a plus 1. Okay, and then of course a special case of that, if a is just n, which is an integer, so if a is n, then I have that the Laplace transform of this power function here, or monomial, right? This is just gamma of n plus 1 over s to the n plus 1. But gamma of n plus 1 is n factorial over s to the n plus 1. All right. So that becomes a special case. All right, so now using that fact, we can find the Laplace transform of this function right here. Okay, we know this is a continuous function, we know it's of exponential order, and so we can go ahead and find its Laplace transform. All right, so the Laplace transform of f of t, this is the Laplace transform of 3t to the 5 halves minus 4t cubed. Now, if we apply the linearity of the Laplace transform, this is 3, the Laplace transform of t to the 5 halves, minus 4, the Laplace transform of t cubed. Then applying our properties here, this is 3, this is gamma of 7 halves or 5 halves plus 1, divided by s to the 5 halves plus 1. This is minus 4 times 3 factorial over s to the 4th power. Right, so if we simplify this, what is gamma of 5 halves? So gamma of 5 halves plus 1, by our property, this is 5 halves gamma of 5 halves. Right. We know 5 halves is 3 halves plus 1. So this is 5 halves times 3 halves. It's 3 halves gamma of 3 halves here. And then 3 halves is 1 half plus 1. So this is 5 halves times 3 halves times 1 half gamma of 1 half. We're going to use the fact that gamma of 1 half is square root of pi. So this is going to give me 15 over 8, the square root of pi. Okay. And then by a similar way, we can now say that this is 3, right, into, we have 15 square root of pi divided by 8 times s to the 7 halves minus, this is 3 factorial, which is 6. This is 24 over s to the 4th power. So this gives us 45 over 8. So we have finally that the Laplace transform of 3t to the 5 halves minus 4t cubed is 45 square root of pi over 8 times s to the 7 halves minus 24 over s to the 4th power. That is our Laplace transform. Okay. So this gives us, tremendous leverage. We can calculate the Laplace transform of polynomials, of power functions. We can find the transform of trigonometric functions, cosine and sine, and we can find the transform of the exponential function. Okay, these are the building blocks for all the other transforms that we're going to consider going forward of rational functions are going to be built on these very basic Laplace transforms. Okay, now finally, let's take an actual piecewise function, piecewise continuous function. All right, so far, all the functions whose Laplace transform we've calculated have been continuous functions. But our theorem says that we can find the Laplace transform for a piecewise continuous function, right? That is of exponential order. So here is an example of a piecewise continuous function that is of exponential order. This function is called the shifted unit step function. Okay, and here's how it looks like. So this is a t-axis, and this is a. Right. And if x is less than a, if t is less than a, our function is 0 all the way up to a. And then if t is greater than a, our function is 1. So this is 1 here. Right. So this is ua of t. This is a shifted unit step function, and is defined in terms of u, which is the unit step function. So this is my t, and the unit step function, it's 0 if you are less than 0, otherwise you are 1. Right, so this here is 1, and this is u of t. So notice that we've only shifted u of t to the right by a to get the shifted unit step function. Okay, so these are the graphs, and this function is clearly piecewise continuous because it has a jump discontinuity. It's just a single jump discontinuity, and it's bounded for all time. Okay, so it's definitely bounded by some exponential function of positive growth. All right. So we can calculate this Laplace transform. So let's go ahead and do that. Right. We are interested in the Laplace transform of the shifted unit step function. By definition, this is the integral from 0 to infinity e to the minus st uat ut. Right. Now, since we are interested in the case where a is positive, then we can break up this integral as the integral from 0 to a e to the minus st right, ua of t dt plus the integral from a to infinity e to the minus st ua of t dt. Okay. Now, when you are less than a, by definition, my shifted unit step function is 0, which means that this whole integral is 0. So the only thing that matters now, and if you are greater than a, my function is 1, by definition here. Right, so this integral just reduces to the integral from a to infinity e to the minus st dt. Right, and we can perform this integration. This is minus 1 over s e to the minus st from a to infinity, right, which if we expand out, this is 1 over s times, this is e to the minus sa plus, so minus the limit as b approaches infinity, e to the minus sp. Okay. Now clearly, if since if s here is positive, right, as long as s is positive, this limit is going to go to 0. Okay, and so my integral converges to e to the minus sa over s for s positive. That's the domain of the Laplace transform. Right. So this is the transform of the shifted unit step function. And this is going to be important down the line. So this is good. We can, given a piecewise continuous function of exponential order, we can find its Laplace transform. Perfect. Okay. Now here's a question though. Can we go back? Given a Laplace transform, can we find a function that generated it? And is that function unique? Because if it's not unique, then we can't really go back, because where do we go to? Right? Remember that in order to define the inverse of a function, your function must be a one-to-one correspondence. Okay. And so the question is that, is the Laplace transform a one-to-one correspondence? Does it map, does it map one function to one and only one transform? In that case, we can always go back. Okay. And the answer is yes. The Laplace transform is a one-to-one correspondence. Right. And if you have two functions, right, that have identical transforms, then we are saying that the two functions have to be identical. Okay, and at least they have to be identical where the functions are continuous. So wherever you have jump discontinuities, we are allowing weird things to happen. But those are, those are only going to happen finitely many times, and so they are not going to affect our integral, right? So as long as these functions are, wherever these functions are continuous, we expect that they be identical. Okay, and so this gives us the leverage to define an inverse Laplace transform, which will take us from a Laplace transform to a function that generated it. All right, and the idea is very similar to how you calculate the antiderivative. When you think about the antiderivative, you may not, before you develop any rule to find antiderivatives, you think about what function do I differentiate to get this function that I have in front of me here. Right. That's the same way we are going to calculate the inverse Laplace transforms. Based on the properties that we have studied so far, the building blocks, right, we are interested in finding the inverse transform of 1 over s plus 5. Right. And so the question is, what function has this Laplace transform? S plus 5. Okay. Now recall that the Laplace transform of e to the at is 1 over s minus a. So if you compare this transform to that, right, you can pick out that, oh, a has to be -5, which means that the inverse transform of 1 over s plus 5 is e to the minus 5t. Okay, now again, conventionally we go from s to t and from t to s for Laplace transforms, right? Just so that we can be consistent with the notation. So that's it. That's how you calculate the inverse transform. You look at the function, and then you try and compare it to a transform that you already know, and then you identify, what function could have given you that transform, and then you have the inverse transform. Okay. This idea of inverse transform is going to be central to our application of Laplace transforms to solving ordinary differential equations. Okay, so that's all I have for you today. Take a look at these practice problems. They're just going to take you through, trying to calculate Laplace transform of different functions, and then trying to find the inverse transforms. The inverse transform is actually more fun, because then you have to look at patterns and trends and compare it to what you already have. There's a table in your textbook that lists the Laplace transform of very basic functions. It's a good idea if you have that handy as you go through problem sets, because it's just going to help you to remember these things very easily. Okay. All right, guys. This is it for today. Look out for my next lecture. In the next lecture, we're going to talk about how to apply all of this to solve ordinary differential equations, and that would require us to build some more properties or some more identities. Right? If we want to be able to solve a more broader class of differential equations, we will need more transforms techniques other than these basics, and so we're going to build on some more techniques for calculating Laplace transforms. Enjoy the rest of your day, and look out for my next lecture. Bye.